Hello friends, in this video I'd like to solve the following problem from the German Federal Mathematical Competition, first round, year 1981, problem number 4. We wish to show that for no prime number p is 2 to the power of p plus 3 to the power of p a perfect power. Perfect power means that it's k to some power l, where l is 2, 3, 4 or greater. My hints for this problem. The easiest way to show that something is not a perfect power is to find a prime q, let's say a prime q, such that q divides our number, but q squared doesn't divide it. Because that would mean that q cannot appear with power greater than 1 in prime factor decomposition. And that would mean that our number cannot be a perfect power. And you should try to guess this number q. And it's not that hard. You should consider values of this sum for small primes. For example, 3, 7, 11. You should see the pattern emerging. Then, since p is a prime, what are the possible values of p modulo 10? And also notice the following two nice coincidences. 2 to the power of 10 is 1025 minus 1, and 3 to the power of 10 is 59,050 minus 1. Well, they are not coincidences, but whatever. So give this problem a try, and I will see you in a minute. Okay, so I hope that you've managed to solve this problem. Here is my solution. First, I wish to consider two separate cases for p equals 2 and for p equals 5. You shall see in a moment why. Well, if p equals 2, then 2 to the power of p plus 3 to the power of p equals 4 plus 9, 13, which is not a perfect power. And if p equals 5, then 2 to the power of 5 plus 3 to the power 5, it's 32 plus 243, 275, and this number is also not a perfect power. So now let p be a prime, but not 2 and not 5. And if you try plugging in values for p equals 3, 7, 11, you will see that every number, 2 to the power of p plus 3 to the power of p, every such number is divisible by 5, but none of them is divisible by 25. So now I wish to consider this sum modulo 25. And one more thing. Okay, maybe not. So let's notice that 2 to the power of 10, as I suggested, it's congruent to minus 1 modulo 25. And also 3 to the power of 10 is also congruent to minus 1 modulo 25. And also, what are the possible remainders of division? So that means that 2 to the power of 10, let's say, take k plus r plus 3 to the power 10k plus r, this number is congruent to plus or minus 2 to the power of r plus 3 to the power of r modulo 25. So now it suffices to check what are the possible values of this expression for r from 0 to 9. But also, let's notice that since p is a prime and it's not 2 and not 5, p modulo 10, well, it can be either, can it be 0? No, it can't, because that would mean divisibility by 10. It can be 1, it can't be 2, because 2 would mean that p is even number, and there is no even prime apart from 2. It can be 3, it can't be 4, because also even number. It can't be 5, because that would mean that our number is divisible by 5. It can be 6, it can be 7, it can't be 8, it can be 9. Okay. And now I will check these three numbers. So 2 to the power of 1 plus 3 to the power of 1, well, it's congruent to 5 modulo 25. 2 to the power of 3 plus 3 to the power of 3 is what exactly? 8 plus 27. 8 plus 27 is 35, and 35 is congruent to 10 modulo 25. 2 to the power of 7 plus 3 to the power of 7. Let me use my calculator, because I don't want to do these tedious calculations by hand. Well, it's congruent to 15 modulo 25. And finally, 2 to the power of 9 plus 3 to the power of 9, it's congruent to 20 modulo 25. In every case, 5 divides 2 to the power of r plus 3 to the power of r, but at the same time 25 doesn't, where r is just this remainder upon division. So that means that for every prime number p, which is not 20, which is not 2, it's not 5 as well, 5 divides 2 to the power of p plus 3 to the power of p, and 25 doesn't. Okay, that implies that 2 to the power of 5, 2 to the power of p plus 3 to the power of p cannot be a perfect power. It can't. And that closes our proof, because we have already considered p equals 2 and 5 in the beginning, and now we know that for every other prime, our sum isn't a prime as well, and that closes our proof. Okay, so thank you for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.